couple of caveats at the beginning of this talk. First of all, I took my instructions to give a mini course aimed at the non-experts. So this is going to be don't think I'm going to be successful at that. It's just that's how I interpreted my instructions. So that's my aim. It will be quite elementary. Almost everything I say dates from at least 35 years ago, though in my second talk I will try to make a few connections with the sorts of things we were hearing this morning and hearing from Kevin, and we'll hear from Kinji later on this afternoon. But today is going to be very elementary. I'm going to start at the beginning. I'm going to start pre-Dennis. So I first met Dennis in 1966, if memory serves, 45 years ago. And I remember thinking of him then, as I still think of him today, as the master of the evocative yet ambiguous phrase or sentence in his papers. So I remember spending hours, days, weeks trying to unravel what one sentence in one of his papers might mean. I could still quote some of them to you, but I don't think I will. Talking to Dennis is still like that today. All right. So I'm going to start with the background, the pre-Dennis background in rational homotopy theory. And it all starts with something, to me anyway, that Ralph alluded to in his talk this morning, the cup product formula for cochains. So let's think about the singular cochains on a topological space. And we have a cup product, so X is our space. We have a cup product pairing. And let me just remind you of the formula which we teach our undergraduates. If you have an alpha cochain and a p cochain and a q cochain beta, and you want to evaluate them on some singular simplex, which is a map of a simplex, let's say, denote the simplex this way. So that should be, well, if we're working over the integers, that should be an integer. And the formula we write down, I believe it's the Whitney formula, but I'm not sure, is you evaluate alpha on the front face, sigma restricted to the first p vertices. You get a number, an integer, and you multiply that by beta on the back. P plus q. And that's the answer. Okay? It's easy to see that many of the algebraic properties that you want, you have. First of all, you have the Leibniz rule. It's completely straightforward. Sorry. Now you have the Leibniz rule. It's an associative multiplication. It has a unit. Which, of course, is just the cocycle in degree 0 that evaluates 1 on every point. But okay, so what does this tell you? This tells you that it induces a ring structure on the cohomology of X, an associative ring structure. What is not clear from this formula is that this ring structure on cohomology is graded commutative. So this is graded commutative in the sense that the class of alpha up the class of beta is, if alpha and beta are cocycles, minus 1 to the pq class of beta up class of alpha. Because this cochain formula does not have that property. If you reverse alpha and beta, you're evaluating alpha on the back face and beta on the front face, and that has absolutely nothing to do with alpha on the front face times beta on the back face. It's a highly non-commutative formula. On the other hand, it does induce a commutative multiplication. When I say commutative, I'll always implicitly mean graded commutative on the cohomology. So this led to a question which must have been extant in the 40s and early 50s. Is there a better formula? Maybe there's a formula that has all of these properties and this one on the cochain level, and then one could see immediately that the cohomology had all these properties. Because in fact, when you prove this commutativity, it's not obvious. You have to do a little work, and we'll talk in a minute about the kind of work you have to do. But maybe this is just not a good formula. There's a better formula. Well, in fact, Steenrod gave the answer to that question, which was, as I've set it up here, there can't be a better formula. And let me try to explain how that goes to you. And it really goes by thinking through how you prove that the ring structure in cohomology is commutative. And this goes back to the idea of a chain approximation to the diagonal. So let's shift gears slightly from an arbitrary topological space to a simplicial complex, or maybe even better, a regular cell complex. So a space is divided up into cells, and say open cells, and the closure of each open cell, well, is a union of lower dimension. The boundary is a union of lower dimensional cells, and the closure is topologically a closed cell, or technically all I need is that it be acyclic. Okay, so a simplicial complex would have that property, but there are many others. So for any topological space, we have the diagonal of x embedded in x cross x. If x is now one of my regular cell complexes, I can replace the singular chains by the cellular chains, which has one z for each cell, and the boundary map's given by just reading off the faces of the cells. Okay? And that computes just as well as the singular homology, singular chains. It computes the usual singular homology or cohomology. So we're going to use then cellular chains to compute homology. Of course, the cell structure on x cross x is simply the cells on x cross the cells on x. So, for example, at the cochain level, I don't worry about infinite complexes, but take finite complexes. This is the cochains on x cross x, and I have the cochains on x, and you sort of imagine using the diagonal map to pull back. The trouble, and here's where the trouble comes, this map is not a cellular map. It doesn't send cells of a given dimension to cells of the same dimension. Just think about what happens in the square. So let x be the interval. This is x cross x. Here's the diagonal. And you see this one cell here on the diagonal doesn't go to a one cell or a linear combination of one cells in the product. Okay? And therefore, you don't have an induced map here since cells don't go to cells of the same dimension. Okay? But that's okay. You can, because of our hypothesis, create what's called a chain approximation to the diagonal, which, if we do it on the chain level, associates to each cell of x. So let C be a cell of x, associates to it an element kc, which is a linear combination of cells of the same dimension, degree. but it actually has to be supported in the closure of C cross C. Okay? So I want to associate to each cell, like this one cell, a linear combination of one cells in this square. Okay? And they have to be consistent with the boundary. Once I associate something to each cell, since I know the boundary of a cell is a sum of one lower dimensional cells, it makes sense to write down the equation. Boundary of the element associated to a cell C is the linear combination of things associated to the boundary. Okay, so I want that condition. And I also want that when C is a zero cell, that K of C is the obvious thing, C cross C. So I start with the zero cells, and the diagonal maps them to zero cells. So that's a good start. And now I have to continue inductively. You can always solve these equations. Inductively, you're given this, and it will be a cycle, and it will be supported in this acyclic thing here, the carrier. And therefore, being a cycle in an acyclic space, it's the boundary of something, and I just inductively build up.
That's why your cells have to be bigger.
That's right. That's the acyclic carrier theorem. Right. Mm-hmm. So that then gives me a chain approximation to the diagonal, which gives me a chain map from the chains on X into, who bought this crummy chalk? Into the chains on X, cross X, which are simply the chains on X, tensor the chains on X. Okay? Now, what does this have to do with cup product? Well, it's an easy exercise from the definitions that if you, in singular cohomology, for example, if you take the pullback of the diagonal map from the cohomology of X cross X back to the cohomology of X, and you have a map here, the Kunith map from the cohomology of X, tensor the cohomology of X, into here, this composition is simply cup product. Okay, so if I use singular chains, and now don't worry about my cellular chains, exterior product here in X cross X restricts along the diagonal to become cup product. Okay. Now, inductively, well, so I have this K of C, which is in the cellular chain complex. I also have the diagonal of C, or C bar, which is in the singular chain complex. So let's think what might happen in the square, this example I started with. My chain approximation to the diagonal might look like this. So the zero cells go here. The diagonal could go here plus here. Or maybe it goes here plus here. Right? But anyway, I have to choose one. There's no natural one to choose. So that's my chain approximation to the diagonal. Here's the diagonal here. That's a singular element. This is a cellular element, and therefore a singular element. And because we're in an acyclic part of the space, there's a homology between them. And just as I built the chain approximation to the diagonal, I can build these deformations or homologies inductively. And so, in fact, the chain approximation to the diagonal is homotopic, or chain homotopic in singular homology to the actual diagonal. So of any cycle zeta, we have a singular homology between the chain approximation to the cycle, that's some cycle in X cross X, and the image of the diagonal. So in particular, they represent the same homology class, and therefore when I pull back under the chain approximation to the diagonal or pull back under the diagonal, I get the same map in cohomology. So this induced map in cohomology from the cohomology of X, tensor the cohomology of X, into the cohomology of X, is cup product for any chain approximation to the diagonal. Okay? All right. Well, what does this have to do with commutivity? There is the switch of factors map. Okay. And that acts on cohomology by introducing a sign. Clearly, T star of a class A in degree P, tensor a class B in degree Q, is -1 to the PQ because of graded commutivity in signs of BQ tensor AP. Okay. On the other hand, if I take this chain approximation to the diagonal and compose it with the switch of factors, the switch of factors leaves my sigma cross sigma invariant. So this is a new chain approximation to the diagonal. Call it K prime. And therefore, it also induces cup product. So we see, without using T, that A tensor B goes to A cup B, goes by T to up to a sign B tensor A, which then goes to that same sign times B cup A. And there's the graded commutivity in cohomology from this acyclic carriers theorem. And you see the real problem here with the non-commutivity expressed in this language is that the simplices have finite extent. And when you think about differential forms, we'll come a little later in the discussion, differential forms are supported at points, and those don't have finite extent, and you have a commutivity in differential forms that you can't quite get in cohomology, in singular cohomology. But you can work close enough to the diagonal that up to homotopy it all doesn't matter. Okay? All right. That's where Steenrod entered the picture. He said, well, yes.
It matters.
Well, yes. It doesn't matter in cohomology. So Steenrod observed that this was just the beginning of an infinite process. So let's think pictorially of the chain approximation to the diagonal as a dot. So the dot is really a cellular map of X into X cross X. Okay? And then I have the switch of factors. So this is my map phi, the chain approximation to the K, I called it. Then I have the composition with K. That's a different chain approximation to the diagonal, but they're homotopic because of this acyclic carriers. They both sit in cell by cell. They sit in the same contractible space, so I can connect them by a homotopy. Okay, so that's some homotopy K1, but of course I can flip K1 to get a different homotopy between the two. And that's now a circle of maps into this neighborhood of the diagonal. But we're still working in an acyclic or contractible region, so this circle of maps extends over a two-disk K2. So there's a two-disk of maps into this neighborhood of the diagonal. But there's no reason not to flip the two-disk. And so on. This process continues forever, and you end up with a cellular map of the infinite sphere cross X into X cross X, cellular, and Z2 equivariant, where the involution is acting by the flip of factors here, T, and simply by the antipodal map on the infinite sphere. This is just the union or direct limit of the n sphere for every n. The n sphere sitting in the n plus first is the equator, and just keep going. So you have the involution here, the antipodal involution. You have the flip here, and by construction, this map is equivariant. and it's a chain approximation to the diagonal. Well, this will induce something on equivariant cohomology. So equivariant cohomology of x cross x, back to the equivariant cohomology of S infinity cross x. But this action, unlike this one, this action is free, and therefore the equivariant cohomology is just the ordinary cohomology of the quotient, which is the cohomology of Rp infinity, that's the quotient of the infinite sphere, plus x. So we have a map here. By the Kunis theorem, let's take Z2 coefficients. This is simply the cohomology of x with one extra generator alpha in degree 1 polynomials on that generator. That's the cohomology of Rp infinity. Now, if I start with a cohomology class here, better not call it alpha, beta, and I can take beta tensor beta. That's an equivariant cocycle. It induces an equivariant cohomology class, which I can pull back. And I get an answer which is expressed as in terms of powers of alpha, and it will turn out to be an expression like this, which we write this way. It's some coefficients, which depend on beta, times the various powers of alpha. And these things are called the Steenrod squares, and they have all sorts of beautiful properties, which are fairly easy to deduce from these definitions. They're natural under maps. Square n of an n-dimensional class is the usual cup square. Square naught is the identity. That's actually, square naught of beta is beta. That's a little hard to prove. And then you have these intermediate squares. And they're non-trivial cohomology operations. So if you had some sort of commutative cochain formula, you could use those commutative cochains to make a more abstract version of this argument and see that all the squares would have to vanish. But in fact, they don't vanish. So these are obstructions to finding a commutative, associative, Leibniz rule cochain formula, and they're non-trivial. So you can't solve the commutative cochain problem, at least mod 2. It turns out there's a completely analogous discussion for any finite cyclic group. You take a product, let's say, of a p, take a product of p x's, you have the z mod p action on the infinite sphere, and you get Steenrod's reduced powers in z mod p cohomology. They work exactly the same way. They're non-trivial. So there are obstructions to solving the commutative cochain problem. But they're finite order. These are Z2 classes, and you can have some ZP classes. There are no analogous infinite order classes, which led to the question, can one solve the commutative cochain problem with rational coefficients rather than integer coefficients? And in some abstract sense, Quillen proved that the answer to this is yes. And I'll talk a little bit about what Quillen did. We'll see it's not as direct a system of cochains as you might hope for, but nevertheless, in some categorical functorial sense, he answered the question in the affirmative. So what Quillen really showed was, Quillen showed the rational homotopy category. I'll say what that is in just a minute. And here he had to restrict to simply connected spaces. Is equivalent to the category of co-commutative co-associative co-algebras. And if you dualize one of these objects, you remove all the co's and you end up with a commutative, graded commutative associative algebra. So rational homotopy theory is completely encompassed in a category of, well, commutative associative algebras. Okay? So what I want to do is tell you, first of all, what I mean by the rational homotopy category, at least for simply connected spaces. And then I'll say briefly, just to give you a flavor of Quillen's argument, to compare with what Dennis had to say later about the same subject. So the idea of rational homotopy theory really goes back to Serre, where he in his proof that the homotopy groups, the higher homotopy groups of spheres are finite. So what we're going to do, we're going to look at the category of simply connected spaces. So the objects are going to be simply connected spaces. And to begin with, we take the morphisms just to be continuous maps. But I want to introduce a relationship. I want to say certain maps are quasi-isomorphisms, and then make a new category where I formally invert the quasi-isomorphisms. Now, this isn't the way you usually do homotopy theory, but in this category of spaces, by the Whitehead theorem and the Raywood's theorem, it's equivalent. So we'll say that F mapping X, so simply connected spaces, well, okay. Let's not worry about that. Maps X to Y is a quasi-isomorphism, means that F star from the homology of X to the homology of Y is an isomorphism, or equivalently, the induced map on homotopy groups is an are isomorphisms. Is that something I need to worry about? Okay.
You made a false statement.
What are you talking about? All right. Well, we're working with simply connected spaces, so usual.
That's what shut off the alarm.
Okay, so these are quasi-isomorphisms. If we were in a category of spaces, homotopy equivalent to CW complexes, these maps could be inverted up to homotopy. But even without that, I can introduce this notion of quasi-isomorphism. And then there's a new category whose objects are topological spaces and whose morphisms are compositions like this, where every arrow going the wrong way is a quasi-isomorphism, thought of as the formal inverse of the quasi-isomorphism. As I say, if we were in the homotopy category, these could be homotopy inverses, and you would work up to homotopy. Okay. So that's one way to think about the homotopy category, at least for simply connected spaces. And this leads naturally to a notion of the Z-mod, the Z localized at 2, or the Q, or any other ring you want containing the integers, homotopy. So I could now define rational homotopy theory. Again, in the category of simply connected spaces, where I now declare that a map X to Y is a quasi-isomorphism if and only if the induced map on rational homology is an isomorphism, or equivalently, the induced map on rational homotopy groups. Okay? The first thing you have to check, and this is what goes back to Serre, is that these conditions are equivalent. So let me just spend a minute on that. Well, we start by computing the rational cohomology of KZN. So KZN is the Eilenberg-MacLane space. It has only one non-trivial homotopy group. That's in degree n, and that group is the integers. Okay? And I want to calculate the rational cohomology of this space. This is a computation that will be crucial later on. And we see that we either get a polynomial algebra on one n-dimensional generator. This is for n even. Or an exterior algebra on one n-dimensional generator when the degree of A is odd. So it's the free graded commutative algebra generated by the rational vector space dual to this thing. So more generally, for any free abelian group, the Eilenberg-MacLane space with that as group in degree n is a polynomial algebra generated by F tensor Q star, or an exterior algebra generated by F tensor Q. Again, depending on even or odd. So it's the free graded commutative algebra generated by the vector space, rational vector space dual to F. Okay?
Is this something that's easy to see, or is it
Yeah.
makes it tough?
Well, it's easy to see by induction. Let me prove this one. You get this one by taking some direct limits. You have to worry a little bit about projective stuff, but I'm not going to get into that. Proof by induction. N equals 1. KZ1 is the circle, and I think we all know the theorem there. In fact, we know it for n equal 2. KZ2, I should have said, these spaces are unique up to homotopy equivalence. Canonical homotopy equivalence up to homotopy if you fix the if you fix the group up to if you fix the group. Anyway, this is CP infinity, and its cohomology is polynomial algebra. Now we just do a little Serre spectral sequence. We have KZN as the fiber of a fibration whose base is KZN plus 1 and whose total space is contractible. This follows from the homotopy long exact sequence, basically. The fibration. So if we know by induction the cohomology of the fiber is what I claim, then we have two cases to think about. We have a spectral sequence. Let's think maybe, do the case when n is odd. We have a spectral sequence whose fiber has two non-trivial rows, one in degree 0, which is just the cohomology of the KZN plus 1. And up here, another copy of the cohomology of the KZN plus 1. And the spectral sequence has to converge to the thing that only has a Q here and zeros everywhere else because the total space is contractible. So there's only one non-trivial differential, and it goes from 0 in n to n plus 1, 0. It goes across here. So it takes the generator here to the generator here, And now you just show by induction using the derivation property of the differentials that the powers of this element all have to be non-trivial and they account for everything. There's your polynomial algebra. There's a similar but slightly different argument when it's a polynomial algebra up here and then there's just one other column and it's killed. Maybe I should just say why this argument doesn't work over Z. I mean, after all, these isomorphisms, the first two work fine over Z. You lose the integral property at the next step. If you go Cp infinity contractible kz3 and you work over the integers instead of the rationals, what happens is here you have the polynomial algebra z, 0, z, 0, z, 0, z, 0, z, generator a squared, a cubed, a to the fourth. And now you start building the thing that's going to be the base. Well, here you have the differential of A. Let's call it B in degree 3, and this is an isomorphism. The differentials are derivations, so the derivative of A squared is 2AB. And so you see these coefficients, these integers coming in. Over the rationals, it doesn't matter. But in fact, you can take this argument and you can estimate, as Serre did, when the first time a prime p will occur in the homotopy groups of spheres. You could just push this argument up and see the first p coming in, and so on. So you can learn a lot of information, but this Leibniz rule starts introducing integers and produces torsion in the cohomology of this thing. Okay. But over the rationals, that isn't an issue, and you get these nice uniform results. It's beginning to indicate rational homotopy theory is a lot simpler than integral homotopy theory. This shouldn't surprise you. The higher homotopy groups of the spheres are completely understood rationally, and they're not at all understood over the integers. Okay, where was I? Yes. So rational homotopy yes, I was trying to indicate why being an isomorphism in rational cohomology and in being an isomorphism in rational homotopy are the same. And I've just done the first computation. So it now follows from this computation that if pi is a torsion group, for example, a finite group, then the reduced integral cohomology of k pi n for any n, coefficients in Q, is 0. Okay. Because you can resolve a torsion group by free groups, and this is a rational isomorphism. So by our computation, a map that in rational isomorphism between these free abelian groups will induce isomorphism of rational cohomology, and so by, again, some sort of spectral sequence, you'll see this can't have any rational cohomology. Okay. So if you have a finite abelian group, it has no rational cohomology. Okay, so now I'm ready to establish this equivalence. Let's go from homotopy statement to the homology statement. Okay. So I have a map F from X to Y. It's an isomorphism in rational homotopy. That means when I turn it into a fibration, homotopy fibration, the fiber has torsion homotopy groups. And therefore, the fiber is made out of putting together these spaces one after another, and each one of them has trivial rational cohomology, so when you stick them all together, you still get trivial rational cohomology, and therefore this map is a cohomology, rational homology isomorphism. Okay. The other way is an interesting one. So now let me go from cohomology to homotopy. So now the map induces an isomorphism on rational cohomology. Here you have to turn the argument around and use the Horowitz isomorphism. So you go to the first place where the map is not an isomorphism on integral cohomology, And there, the relative the homotopy group of the fiber and the homology of the fiber will be the same, but it's a finite, it's a torsion group. And therefore, that first homotopy group of the fiber is torsion, and therefore it has no rational cohomology. So rationally, it makes no difference, and you keep going inductively up. And you prove all the homotopy groups are finite, or are torsion. So that's a brief sketch of this, that these two notions of rational homotopy theory are the same. So rational homotopy theory is the rational homotopy category is the category whose objects are simply connected topological spaces and whose morphisms are chains of morphisms alternating between direct and reversed, where all the reversed are, quote, formal inverses of these quasi-isomorphisms, of maps that induce isomorphisms on the rational homology.
What goes wrong in the argument you can just sketch if the spaces aren't simply connected?
It's not even true over the integers then. Think about, there are lots of three manifolds that are k pi 1s, glue two knot complements together, that have the homology of the three sphere. You can map them to the three sphere. I mean, you have the fundamental group has non-abelian parts. It acts on the higher homotopy groups in a very complicated non-abelian way, and you don't have the Hurewitz isomorphism. That's not a problem that's solved by going to Q. Okay. Okay, so here's Quillen's isomorphism. The Q homotopy category is equivalent to the category of Q differential graded co-algebras. So we're going to have a sequence of categorical isomorphisms, which in fact have explicit maps and adjoint functors that give the equivalences of categories. There's some complicated algebraic structures here in the middle. I'm going to write them down. If they don't mean anything to you, you can just tune out for 3 to 5 minutes while I do this, because I'm not going to pursue this line. I just want to give you a sense of the nature of this isomorphism. Okay, so the first thing you do is you go by con to what's called the simplicial set. Simplicial sets. You take a space and you take its, well, basically its singular complex. This is a so-called simplicial set. In degree n, you have all the continuous maps of the n simplex into X. That's a huge uncountable collection. You take the free abelian group, well, no, take that collection. That's a set. On that set, if you have a map of a simplex n, the n simplex has n plus 1 faces, and you could restrict the map of the n simplex to any one of the faces. So from the set of n simplices, you have n plus 1 maps from an n simplex into the space into n minus 1 simplices into the space by simply restricting to the various faces. These are called the face maps. You also have degeneracy maps. If you have an n minus 1 simplex, you can collapse the n simplex onto it so the vertices go to the vertices in an increasing fashion. So one of them gets doubled, and there are n minus 1 places where you could double. Those are the degenerate simplices. If you had a map of the n minus 1 simplex into the space, you could collapse the n simplex onto it in any one of these ways and then map in. Those are called the degenerate simplices. These things satisfy some obvious algebraic conditions that are just related to the way faces and degeneracies work. And that's called a simplicial set. And we could have a simplicial object in any category. Each one of these, for each n, we would have an object in the category, a group, an algebra, whatever. And then we'd have to have morphisms in the category for the faces and for the degeneracies, and they would have to satisfy the algebraic axioms that I haven't written down. That would be a simplicial, whatever, group. Okay. So Kahn's simplicial set was well known to recreate the homotopy type of X. In fact, as the geometric realization, and the nicest form of it was given by Milner, you simply take all the simplices in dimension n, you forget the degenerate ones, you only use non-degenerate ones, and you stick them together using the face relations, and you build a simplicial complex that's weak homotopy equivalent to your original space. So this is a good equivalence. Then there's something called the Kahn group functor that goes to simplicial groups. So now instead of having sets at each level, we have a group. And this is an analog of what Ralph was talking about this morning, the chains on the loop space. This is a model for the chains on the loop space. Okay. Well, you can go from simplicial groups to simplicial Hopf algebras. You just associate to a group its group ring, and we're working over the rationals now. You actually have to complete it with respect to the augmentation ideal, but let's not worry about that. Inside a Hopf algebra, so a Hopf algebra is an algebra. It has a multiplication. It also has a co-multiplication. So inside a Hopf algebra, you can look at the primitive elements, the things that under co-multiplication go like this. Those are the primitive elements. And they make a Lie algebra. So we have a simplicial. Everything here is simplicial. So we get a simplicial Lie algebra by taking the primitive elements. Well, and we're getting there. Now there's this great Eilenberg-Zilber shuffle that turns a simplicial object, like this Lie algebra, into a differential graded object. So then you get differential graded Lie algebras by the shuffle. It's really a fantastic map. Okay, so we started with our space. We looked at all the simplices in the space. We did some sort of loop construction. We ended up in Hopf algebras, Lie algebras, simplicial Lie algebras, differential graded Lie algebras. And then if I want to get a differential graded algebra, I simply take the free graded commutative algebra on the graded Lie algebra. That's the underlying algebra. And then well, no, I'm going to take the dual, sorry, dual. And then I want to take the differential to be the sum of the dual to the derivative in the Lie algebra and the graded Lie and the differential graded Lie algebra, and the dual plus the dual to bracket. The fact that this squares to 0 is three equations. This thing squares to 0 because the original differential did. This thing squares to 0, that's the Jacobi identity. And the fact that the differential is a differential homomorphism of Lie algebras says that the commutant of these two is 0. Okay? So there's a differential graded commutative algebra. That's Quillen's isomorphism. Now, it has some cochain-esque features to it, right? I mean, we're working on all the simplices. And then we do all these algebraic constructions. It's not completely clear in what sense these are cochains. But Quillen did prove that at each step you're getting an isomorphism of Q of categories over Q. And so in some abstract sense, he solved the commutative cochain problem. All right, well, that's the background. That was supposed to take 20 minutes. And this is where Dennis comes into the picture. And I think here I'm putting thoughts into Dennis's head. He's never told me this, but I'm imagining the first thing he said to himself was, look, there's a much more natural and easy way to get from a simplicial complex to a differential graded algebra. Take the differential forms. That was probably one thought. And the second thought, which led to this is the whole algebraic theory, was for the various, well, so one consequence that's got to have is often in geometric situations you know something about the differential forms, and from that you often deduce consequences about cohomology. Well, then I ought to be able to deduce consequences about homotopy theory if I'm using the differential forms rather than this huge abstract machinery. So it ought to have nice geometric applications if I can use the differential forms instead of this stuff. And secondly, I want to build what he called the minimal model to have a much better handle on what rational homotopy theory looks like. What's its structure? What's its nature? What are its important invariants? So again, that's something you could have done over here. But I think those are the two main themes of his excursions into rational homotopy theory. So we have two problems when we think about differential forms. One, on the face of it, they're only defined for smooth manifolds. And two, they're defined over R instead of over Q. But it's easy to remedy both problems. Let's go back to a simplicial complex. So it's got a bunch of simplices. Let's concentrate on one of its simplices, delta n. And let's write down a natural differential algebra of forms on delta n. Well, remember delta n sits inside Rn plus 1 with coordinates, let's say t0 to tn, and it satisfies summation ti equals 1, and ti is greater than or equal 0 for all I. Okay? So the 1 simplex sits in R2, the 2 simplex sits in R3. Okay? So what differential graded algebra should we associate? So the algebra of rational differential forms on this n simplex, well, we'll simply take the polynomials on the variables t0 to tn, but I have to put in this relation, summation ti equals 1. So those are the functions, just polynomial functions on the simplex with respect to the natural coordinates. And then I have to put in the differentials of these coordinates. And again, I have to add the relation, which is obtained by differentiating this relation. Okay? So this is a natural algebra, differential graded algebra associated to the simplex. It's easy to see that its cohomology is trivial except in degree 0. And it's also easy to see that it's natural with respect to linear maps. So if you have a linear map from one simplex to another simplex, you have an induced map on the rational differential forms. Okay? So that's what we do for an individual simplex. What do we do for a simplicial complex? Well, we have to put a differential form on every simplex. They should all be of the same degree, and they should be compatible when we restrict from a simplex to a face. So the K forms, rational K, the polynomials in the exterior algebra are over the ground field Q. Thank you. So this will be collections of K forms on sigma as sigma ranges over the simplices. So one form for each simplex with the property that anytime tau is a face of sigma, omega sigma restricted to tau is omega tau. So a function, zero form on this space, is simply a continuous piecewise polynomial form. It's on each simplex, it's a polynomial form in the coordinates of that simplex, and it's continuous as you as you move around the space. Okay? The higher differential forms don't have that continuity. So let's think about a one form on the circle, which let's say is a union of 3, which is the boundary of the simplex. So let's think about a one form on this space. So X is simply the 3 intervals. Okay. Well, it'll be a one form here, a one form here, and a one form here. And what are the compatibility conditions? The compatibility conditions are this form and this one have to restrict the same at this point. but one forms on the point are trivial. So this is no condition whatsoever. So it's 3 arbitrary one forms, one on each one simplex. Okay, and that's what happens higher up. These forms don't really fit together to make a continuous object. There's no way in a simplicial complex to compare normal directions in one simplex along a face to normal directions in the other. They're just in different worlds, and you don't try to make that kind of comparison. Okay. Well, it's an easy little lemma that, well, this is a differential graded algebra, and it computes the cohomology, rational cohomology of X. And in fact, even better than that, if this is a cycle, if this is a simplicial cycle, well, no, say it this way. There's a map from the differential forms into the simplicial cochains given by integration. If you have a k form, you want to get an integer on each k simplex, you simply integrate that form over the simplex, which is a compact region in space. You just integrate the polynomial form. That commutes with D and is an isomorphism in cohomology. So this is, in fact, this is a chain map inducing an isomorphism in cohomology. So here are some commutative cochains over Q. Okay.
How obvious is it that at the level of cohomology the product is
I guess not, but we could go back to this diagonal argument. And
A local set of axioms for it,
which probably are the axioms that say you can make that diagonal argument work.
What was the question?
Why is this an isomorphism of rings? So,
John, you can do better. Instead of using just the forms, use on the simplex, use the forms tensor the cochains. You get the cochains, and realize it the same way. Then you get morphisms of algebras, which are equivalences.
okay. Not sure I understood all of that. Anyway,
So we solve the commutative cochain problem.
yep. Use differential forms. Okay. One remark. What's the connection to smooth forms? And the answer is that if you're willing to pass from Q to R, this gives an equivalent differential algebra associated to a smooth manifold. So take a smooth manifold and take some C1 or C infinity triangulation. Okay. Then we have various algebras of forms. We have the C infinity forms on the manifold, the usual de Rham complex. We have the rational differential forms on X. And we can put something here, piecewise C infinity differential forms on the manifold. So this makes reference to both the smooth structure on the manifold and the triangulation X. Okay. These guys are in particular piecewise smooth. So by extending scalars, I get a map here. Any smooth form is piecewise smooth. Easy arguments, simplex by simplex, show that these induce isomorphisms in cohomology, and therefore the C infinity forms on M and the real form of the piecewise smooth forms on a smooth triangulation are equivalent in the category of differential graded algebras up to quasi-isomorphism. Okay? So we've got a nice solution to the commutative cochain problem, which is more geometric and in particular fits better with smoothness when we have a smooth manifold. I have a question. been 40 years since I've thought about this theory. No. I learned about it 40 years ago. It's been 35 years since I've thought about it. And a lot has happened, but I'm not aware that anyone has ever shown Quillen's equivalence. So, question. Is Quillen's equivalence equivalent to Sullivan's equivalence? Surely if you trace through all this stuff, you ought to be able to prove that these give the same, up to natural isomorphism, equivalence between the rational homotopy category and differential graded algebras over Q. But does anybody know that that's a true theorem?
Yes.
Okay. I mean, how could it not be? Is there a reference for a proof?
Well, that I couldn't give you. There is, but I don't know what it is.
So, question. Theorem. Somebody's theorem. Okay. All right. Let me just finish briefly by a remark about the difference between rational and real homotopy theory, which we're beginning to see here because we're seeing it in differential algebras. You might say, oh, what's real homotopy theory? Real homotopy theory is simply that the map induces an you say a quasi-isomorphism is when a map induces an isomorphism on real cohomology or real homotopy. Those are equivalent conditions. But guess what? That's rational homotopy theory, because a map between spaces induces an isomorphism on the homotopy group's tensor R, if and only if it induces an isomorphism on the homotopy group's tensor Q. So that's not the right definition, because those notions are not equivalent. Think about simply connected four manifolds. They're given by a quadratic form. The rational equivalence is the rational form of the quadratic form, and the real equivalence is the real equivalence of the quadratic form, and those are not the same. So you cannot define real homotopy theory naively the way I defined rational homotopy theory. And with that, I'll stop. Tomorrow I'll talk about Dennis's construction of the minimal model, what that shows you about rational homotopy. Well, first of all, how it's connected to rational homotopy theory directly, how you read off the homotopy groups, how you read off the Whitehead product in homotopy, and so on. How you read off the k-invariants of the space. And then on the last day, I'll start with the geometric applications to classification of manifolds up to finite ambiguity, and applications to algebraic varieties, Kähler manifolds, and so on. All right. Questions? Yeah, that's right. So you're right. I should have said that. The fact that this is a chain map is Stokes' theorem. The fact that it's an isomorphism in cohomology, you will prove one simplex at a time by induction.
Take differential forms of integer coefficients, and when you differentiate d of x to the n and x to the n minus 1, so it's still an integer. So you still get a differential graded algebra over the integer.
Well, what about, so which form of the exterior algebra are you taking? Yes. I mean, think about the symmetric algebra. I'm a little more familiar with that one. You can either take the quotient mod xy minus yx, or you can do this symmetrization, you know, what's it called, polarization, where you put in an n factorial. But when you think about how differential forms evaluate on two tangent vectors, you got to put a half in there for the skew symmetry. I mean, how would you evaluate? I mean, this is something I never understood. I said, what's the formula for dx wedge dy, dx1 wedge dx2, evaluated on d by dx1 counter d by dx2? Probably 1, right? But the only way you can get, is it 1? Yeah.
Well, why do we care? I mean, for a second, why
Well,
don't
we have, oh,
so why don't we just take the symbol dt1, dt2, wedge them together, and work over these? I mean,
Dennis?
sitting inside the range.
Dennis, when you differentiate a polynomial, it's no longer a cyclic. Same thing as with the Algebraic plane spaces.
Right,
You
so he's
differentiate
saying-
polynomials into the exterior guy, you differentiate x cubed, you get 3x squared dx.
right, same point I was making about the cohomology of KZ3. So when you differentiate
Yeah.
so if you took polynomials on x, consider the exterior on dx, it wouldn't be contractible.
So your answer is that when you write this down, it doesn't give a zero correct answer on the simplex, so you couldn't prove de Rhomb's theorem.
Right.